Okay, ready? Ready to continue? Okay, so remember, like in chapter 2, we looked at the limit of the difference quotient. That was the derivative. And then in chapter 3, we discussed differentiation rules. Now we're ready to learn how to find the area under a graph for any function, not just for those three, linear, quadratic, and cubic. But first we have to talk about what it's called. This is a major theorem, one of the biggest in this course. Fundamental theorem of calculus.
You said this is 5.7.
It's in 5.2. Let me see where it starts. I don't present this in that order. I need, no, actually this is in 5.3. I don't present chapter 5 in their order. So fundamental theorem of calculus, it has two parts, part 1 and part 2. And I would like to start with part 2. It doesn't matter how you want to name it, but I think in this book, yes, in this book, part 2 is what I want to start with. Okay, ready? So just in case you want to look, on page 391, just in case, you don't have to. Okay. If f of x is a continuous function on the interval a comma b, then the area under the graph of f of x is, what is it? Correct. But what is it? Is the limit of the Riemann sum, right? From delta x, f of xi, from I equals 1 through n, on the interval a comma b. And there is another way. So here it is. It's still a sum. But this time, it's not this notation, but is this notation, but we want to make it more fancy, and we're going to use this notation. But it's still s, and it's still sum, but it's this notation. And we call it the integral. And actually, it's called the definite integral. There are two different integrals. So this is the definite integral from a to b. Basically, this replaces the limit and the sum. These two are here. But what do you think I'm going to put? Exactly what we had before. We had delta x times f of xi. Okay, this time we're going to write f of x times dx. Because we know from a long time ago that dx and delta x mean the same thing, and they're measured in the same way, and they're always equal. So the area under the graph of a function, f of x, that is continuous on the interval a comma b, is the integral, the definite integral from a to b, from base times height. Delta x is the base of the rectangle, the width of the rectangle, and f of x is the height. Exactly the same thing. Here we had delta x, f of xi. Here we have f of x times dx. How do I calculate this? This equals, what is the antiderivative of f of x denoted?
Big F.
Thank you. A vertical bar from a to b And this will always equal f of b minus f of a.
Seems easier.
It is way easier. Way easier. So this is fundamental theorem of calculus part 2. If a function is continuous on the interval a comma b, then the area under the graph, and what happens when it's not continuous, you have to wait till calc 2. So if f of x is a continuous function on the interval a comma b, then the area under the graph of f of x is denoted by, and it's exact. This piece is replaced by this symbol, still an s, but an elongated s. So the definite integral, the integral from a to b, these are the limits of integration, from the same sum of the same rectangles, the areas of the same rectangles, base times height. However, how is this determined? Is by finding the antiderivative, the most general antiderivative, evaluated at upper limit and subtracting when you evaluate at the lower limit. And this is fundamental theorem of calculus part 2. Now we will be able to calculate almost everything, not just linear, quadratic, cubic. Almost. Some of the integrals we will not be able to. We may be able to approximate them, but we will not be able to. Now, what is this? Question. Is this a function or a number? Do you think it's a function or is it a number? Of course it is a number. Is the antiderivative calculated at a number b minus the antiderivative evaluated at a number a. So, of course, it must be a number. All our areas were a number, right?
Where we get the conditions to go into those.
Very good. Very good. Exactly.
Can we practice one of the problems that we already did?
Exactly. Yes, please choose. Awesome. I don't trust anything myself. So I love you for saying that. Okay, which one?
The cubic that's on the 3x.
Oh yeah. You mean this one? We didn't determine this one.
One before.
Okay. So what was it?
3x plus 2x squared.
Oh, you have the function from me, so I don't waste your time. Okay, very good. So we want to find the area from which to which?
0 to 3.
0 to 3 from, we're going to have plenty of examples. That's what I'm going to do for the next half an hour. So, but this is a very good point. From what?
3x cubed plus 2x squared.
Let me make a few things clear. When we calculate the definite integral, we have to have the limits of integration. You have to have dx, and you have to have a function. Oh, none of these pieces can be overlooked. Okay? The integral symbol, the lower limit, the upper limit, the function, and dx. Okay? Good. So let's find the most general antiderivative of this. So it's 3x to the 4th over 4 plus 2x to the 3rd over 3 plus 4x. Is this clear? From 0 to 3. So like in 4.9, that's why I couldn't do this without 4.9, right? So like in 4.9, the antiderivatives, we determine the function whose derivative is this. We determine the function whose derivative is this. And we determine the function whose derivative is this. So this is the uppercase f. This is the lowercase f. And this is the uppercase f. So I was given this. I determined this. All I have to do now, plug in everywhere 3 and subtract when I plug in everywhere 0. Thank you for choosing this because I don't have to plug in 0 because when I plug in 0, what is it? 0. So I only have to plug in 3. So 3 times 81 over 4 plus 2 times 27 over 3 and plus 12. Is this a little bit easier than the previous one?
Forget about the other. 90.75.
So what is it? How much?
90.75.
But what about the other one? We didn't calculate 90.75. What was the other one?
90.75.
Okay, very good. Okay, now we're ready to practice this. Ready?
So what about the constant, the plus c?
Awesome question. Awesome question. Very good. So the integral from, the area, the integral from a to b from f of x dx is f of x plus c, correct? Yes? From a to b. Let's plug in b. Minus. Let's plug in a. F of b plus c minus f of a minus c. F of b minus f of a. Because it goes away. Yes. Very good question. Ready to practice this? Okay. So we are calculating definite integrals. And the number and the answer has to be a number. Okay. On page 395, let's choose anything you want from 19 through 44. 19 through 44 on page 395.
31.
31 it is. 31. Very good. The integral from 0 to pi over 4 from secant squared t dt. Well done. So, which function prime is secant squared t? Very good. Tangent t from 0 to pi over 4. Please plug in pi over 4. It's the easiest angle. It's 45 degrees. And sine and cosine are the same. So what can tangent be?
1.
Thank you. Now plug in 0, please.
0.
Exactly. Thank you very much. Now let me choose. Ah, 42. The integral from 1 over 2 to 1 over the square root of 2 from 4 over the square root of 1 minus x squared dx. The definite integral requires the symbol, requires the lower limit, requires the upper limit, the function, and dx. All have to be present for a definite integral. I hope you would agree with the following. You have to agree because this is exactly what we did with a summation, with a sigma notation. We took the constant, the factor outside, right? We had the sum of 3 over n, and we took 3 over n outside because it didn't depend on x, on I in this case, in that case, and on x here. Good. Now I have to dig deep because I have to think and I have to find a function whose derivative is 1 over the square root of 1 minus x squared.
Square root of 1 minus x squared.
Say it again. Thank you. Arc sine x from 1/2 to 1 over the square root of 2. Thank you. Remember, we have to remember those functions. Arc sine prime is 1 over the square root of 1 minus x squared, and arc cosine prime is negative 1 over the square root of 1 minus x squared, and arc tangent prime is
1
over
1 plus x.
Oh, awesome. Thank you. Very good. So now we have for arc sine of 1 over the square root of 2 minus arc sine of 1/2. And the answer must be in what measurement unit? In calculus, always. Thank you. In radians. Okay, remember 1 over the square root of 2 is the square root of 2 over 2. Which angle has sine the square root of 2 over 2? Thank you. I just said to give me the answer. He said it. He said it in radians, and he gave me. Okay, that's okay. Minus. Which angle has sine 1/2? It's the tiny one. 5 or 6 indeed. So I have to find the least common denominator, which is 12. Have to multiply 2 and 3. So 2 minus 3 is negative pi. So it's negative pi over 3 after simplifications. Very good. Now here's a property that Joey already told us about. I thought I would disclose it to you, but he did. Okay. So let's take a look at this function because I want to practice this. This is a function f of x. And let's say this is the interval a, b, c. This is the area. It's a continuous function. And this is another area. And if I want to determine the area, which is the integral from a to c from f of x dx, I can split it into two integrals. The integral from a to b from f of x dx, and the integral from b to c from f of x dx. And I have an application of this right now. Ready? Okay, let's look at 44. Same page. We're given a function which is f of x, and this is 2 for negative 2 to 0, and 4 minus x squared for 0 to 2. We're asked to find the integral from negative 2 to 2 from f of x dx. How will you address that issue or problem?
Integral from negative 2 to 0 plus the integral from 0 to 2.
Yes, perfect. Assuming the function is continuous, I should always check that. So at 0 from the left is 2. At 0 from the right, okay. So it's not continuous on the entire interval, but it doesn't have to be. It has to be continuous on pieces. So negative 2 to 0 plus 0 to 2. This integral exists as long as the function is continuous, and this one can be determined using fundamental theorem of calculus 2, part 2, if the function is continuous. So from negative infinity to 0 to dx, and from 0 to 2, 4 minus x squared dx. This is continuous between negative 2 and 0. I can calculate it like this. This is continuous between 0 and 2, and I can calculate it. So this will be 2x from negative 2 to 0, and then plus 4x minus x cubed over 3 from 0 to 2. Now we have to be very careful because each integral is by itself, and I have to plug in 0, and I get 0, and then minus when I plug in negative 2. 2 times negative 2. Plus When I plug in 2, I get 8 minus 8 divided by 3. Minus, when I plug in 0, I get 0. Is this okay?
So you're saying that that's going to now be -2 times -2?
Yes. When I plug in 0, I get 0. But the formula requires minus when I plug in the lower limit.
Okay.
So then plus, when I plug in the upper limit, I get this. Minus, when I plug in 0, I don't have to write anything because it's 0. So this is 4 plus 8 minus 8/3, which is 12 minus 8/3, or 36 minus 8 over 3, or 28 over 3. Any questions? Any questions? Yes?
On the first interval, that would be below the x-axis. Like you said, that's negative area,
Yes.
but you're still adding.
But, so you mean the result of this?
Yes.
So this is, if you graph, very good question. Thank you, very good question. Now you have to graph the function. The function is this, y equals 2. The interval is between -2 and 0. So obviously the area must be 4. Base times height, 2 times 2. So it depends on where the graph is. But for this case, the graph was above the x-axis.
Not the graph of 2x.
No, not the graph of 2x. Because we are determining this, the integral of this. We are determining the area of that under the graph of 2 between -2 and 0. Very good question. Is this okay? Okay. Now I would like to look at odd and even functions on symmetric interval. What do I mean by symmetric interval? -2 to 2, -4 to 4, -5 to 5. That's a symmetric interval. So here's an odd function. Can you think of any odd function? X cubed. Awesome. Very good. So between -a and +a. And here's the graph of an even function. Between -a and +a. Can you think of a?
X squared.
Good. Perfect. We want to determine the integral from -a to a from x cubed dx. And then we want to determine the integral from -a to a from x squared dx. Notice one thing. What do you think the answer will be here? Symmetric interval, odd function. Exactly. Because this is a positive area and this is a negative area, and they are equal because it's symmetric interval and the function is odd. Just symmetric interval and not odd function is not going to be the same.
So the other would be 2.
Exactly. 2 the x squared dx from which limits? Say it again. Exactly. Now, from what we've covered so far, would you prefer to calculate the area from -a to a, or twice the area from 0 to a? Exactly, because this simplifies things a lot. Good. So please remember, two conditions have to be fulfilled. The interval must be symmetric and the function odd to get 0. And symmetric interval and the function is even to get twice that. Okay. Always, at any point in time when you calculate an integral, you must check that the function is symmetric, is continuous on that interval. So let's take a look. The integral from -1 to 4 from 1 over x dx. The answer is no. I cannot use the fundamental theorem of calculus on this one. For this one, I have to wait till Calc 2. Do not use the fundamental theorem of calculus part 2. Do not. I'm sorry? To show the, oh, yes, what happens in Calc 2, this is an integral that will have a limit in front of it.
It's not.
And we are talking about convergence, if it converges or not. Yes.
Doesn't it have a limit in it?
No, this does not.
Oh, no.
No, very good question. If you remember, I said that this symbol replaces these two.
Yeah. Oh, okay.
So this symbol replaces these two.
Well, I think you were saying that. I was thinking integral that incorporates a limit, is a limit over some. That's why I was thinking that that's.
Right, but because this is, you cannot use the fundamental theorem of calculus part 2. This will be, if it converges, it will change into two integrals.
Oh, okay.
Yes, it will be an integral from -1 to 0 from 1 over x dx plus the integral from 0 to 4 from 1 over x dx. But this, if it converges, it will be a limit. And this, if it converges, it will be a limit.
Okay.
Yes. Yeah. Very good. So now I would like to practice this with a couple of examples. And they are I need you to remember this, and I am sure
56.
which page.
395.
Okay, let's take a look at 395 if you found one. And you said
What A B not.
I'm looking for what even the symmetric angle. 56 could be right. Oh, it's not even side.
okay.
Don't listen.
I found it. 20 on page 417. The integral from -1 to 1 from sine x over 1 plus x squared dx. Every time I see a symmetric interval, I will always check whether the function is odd or even. The interval is symmetric, is between -1 and 1. So if you are curious about this, you can, I'll tell you where it is. These are called improper. This is called an improper integral. Improper integral.
When you split it up, or just that
No, this one.
one.
Improper integral. But you, as I said, you have to wait till Calc 2.
Oh, okay. Okay, we'll wait for it.
Good. So now I look at this function. The function is sine x over 1 plus x squared. How do I show or find or determine whether a function is symmetric or not? What do I have to determine first? Yes. Very good. Awesome. Thank you, Paul. F of -x. So sine of -x over 1 plus -x to the second power. The denominator is the easiest to talk about immediately. Does that change anything?
No.
No, it still stays at 1 over 1 plus x squared. But what about sine negative x? Is sine a symmetric, an odd function or an even function? It's odd. So this is negative sine x or negative sine x over 1 plus x squared, which is the opposite of f of x. And this is absolutely typical. When f of negative x equals the opposite of f of x, let's take a look. It's going to be 0. But I have to write two things. Since the interval is symmetric and f of x is odd. Since the, yes, any question, John? Okay. Very good. Any questions?
Is that a theorem of somebody? Or a rule?
Which one?
This symmetric, just the odd
Yes,
symmetric
if the interval is symmetric and the function is odd, the answer is 0.
No, I was just asking if it's named after somebody.
No, no, not that I know of. No. Okay, here's another. 17, on page 417, the integral from 1 to 5 from dt over t minus 4 squared. What can we say about this?
In the even, it's not symmetrical.
Okay, so it cannot be, I will not even think of looking at odd or even property if the interval is not symmetric.
Right.
So what can we do now?
Still like natural law.
Why?
Because 4 minus 4 is 0.
Exactly. Because it's not, the function f is not continuous on 1 comma 5. When the function is not continuous on 1 comma 5, this is an improper integral. Okay,
So then we can't solve it.
we cannot use the fundamental theorem of calculus. Yes, we cannot. Okay, so far we talked about what it's called the definite integral, and the answer was a number. Very good. Now let's talk about indefinite integral. We have what it's called an indefinite integral, which does not have limits of integration. And therefore, the answer will be a number or a function.
Function.
Exactly. So, the integral from f of x dx, what do you think this will be? Still, the antiderivative plus a constant c. It's just that it will be a function and not a number.
Oh, because there's no.
Because there are no limits of integration. Perfect. Awesome. Very good.
When you say no limits of integration, there's nothing on the top or the bottom of the S.
These are the limits. There is no interval. If there is no interval, we are looking for a function. Ready? Okay. Let's go back now.
395.
Which one?
Page 395.
Okay, let me take a look at 395. Let's see what you want from 395. Yes, I'm ready. Which one?
Can we go with the same one that we did last time?
Yes, which one?
Without the,
Oh, yeah, these are hard. How about dt over t minus 4? I guess that's without.
Which one are we looking at? All these are not indefinite integrals.
Wrong page, sorry about that.
That's okay, no problem. Which one? Okay, I recommend page 404 at the top. Yes, I'm ready. Which one?
How many sections have we gone over?
I'm not presenting chapter 5 in the same order. I will cover everything and you'll have everything.
Let's do 16.
We want to do 16. Very good. Awesome. Well done. 16 on page 404. And this is the integral from secant t multiplied by secant t plus tangent t dt. Perfect pick. Is this a definite or an indefinite integral? Indefinite indeed. Perfect. I don't really like this product, so I'm going to distribute. So then I have the integral from secant squared t plus secant t tangent t dt. And now I'm going to ask myself, what function prime is secant squared? Plus, I'm going to ask myself now, is there a function whose derivative is secant tangent?
Yes.
Secant t plus a constant. So this is the function, is the uppercase f plus the constant, the most general antiderivative. Ready? Okay. 11 it is. Perfect. Good pick. 404. The integral from x to the third minus 2 the square root of x, everything divided by x dx. Perfect pick. What do you think I'm going to do first? For sure. Something many of you did not do on the test with that function. Simplify. Yes. You always want to simplify. Always. So then I have the integral from x to the third over x minus 2 the square root of x over x dx. Therefore, I have the integral from x squared minus 2. So this is power 1/2 minus 1. So this will be x to negative 1/2 dx. This is what I want to integrate. So power 1/2 minus 1 is negative 1/2. And this is straightforward. X cubed divided by 3 minus 2 x to negative 1/2 plus 1 over negative 1/2 plus 1, and I'll come back and correct that, and plus a constant c. So x cubed over 3 stays. Now this is 1/2, and I have to flip it. So it's minus 4, the square root of x plus a constant c. And this is the most general antiderivative of the function x cubed minus 2 the square root of x over x. Question. Going back for a moment to the definite integrals. We calculated this one. Is there any way I can check? I can only hope that it's correct.
Put it in and make it get 0?
Yep. No, by hand I can't check this. Question. Is there any way I can check this answer? Always. The definite integral we can always check. Okay.
But isn't that the indefinite?
The indefinite. Did I say definite?
Yeah.
Sorry. I strike that. The definite we cannot check unless you put it in the calculator or in a computer software. Then you can check. But by hand we can't. Can I check the answer of an indefinite integral? Always. So here's what we concluded. We concluded the integral from x to the third minus 2 the square root of x over x dx was x cubed minus 3 minus 4 the square root of x plus a constant c. Correct? This is what we came up with. And now I want to talk about, I'm continuing this. I want to talk about the fundamental theorem of calculus part 1. FTC part 1. How will I show that the integral of f of x dx equals that function?
Take the derivative of
Apply the derivative. Differentiate both sides. Yes. So I will differentiate the left-hand side, and I will differentiate the right-hand side. Ready? And now, FTC Part 1 reads, differentiation and integration are operations. One more word. Thank you. This is what fundamental theorem of calculus part 1 shows. And I'll show you with slightly more sophisticated examples, but this is what I need for now, this moment. Fundamental theorem of calculus part 1 says that differentiation and integration are inverse operations. So, if I differentiate an integral, I get the function. If I integrate a derivative, I get the function. So here we differentiated an integral, and we got the function. Let's see what we get on this side. So it's a question mark. 3, right? I differentiate this. Okay. 3x squared over 3.
Wouldn't it be x to the 4th over 4?
I'm differentiating.
I meant as the,
You mean on the side?
no, on the other side.
On the side?
Yeah.
So when I differentiate x cubed over 3, I bring down 3, subtract 1 from the power.
Oh no, he's saying when you originally got the derivative of the function.
Okay, so let's go back. Let's go back. So I had x cubed minus 2 the square root of x over x, and I split into 2 fractions. X to the 3rd over x, that gave us x squared, and negative 2 the square root of x over x, which gave us negative 2x to negative. That's okay. I'd rather go back and check. You may see something that I don't. So now, which function prime is x squared is x cubed over 3. Then minus 2 gets copied. So x to negative 1/2 plus 1 over negative 1/2 plus 1 plus a constant c. So now, this was 1/2, but it's 2 over 1, so I have to multiply by 4. X to 1 minus 1/2 will be the square root of x plus c. Is that okay?
Yep.
Okay. Good. So let's continue then. We differentiated an integral, and we got the function. Now I'm asking myself, does this equal the derivative of this? So 3x squared over 3 minus 4, 1 over 2 the square root of x, and plus the constant prime, which is 0, correct? Okay, don't look on this side just yet. So I have to find the least common denominator, right? So I simplify. So the least common denominator is 3 the square root of x. Okay, so I need to multiply. So 3, oh, sorry, I talked too much. Okay. So the least common denominator is the square root of x. So this is x squared, the square root of x, and minus 2. So far, so good? Okay. So now I have to rationalize. So I have to multiply by the square root of x over the square root of x. So then I will get x squared times x is x cubed minus 2 times the square root of x divided by x. Okay, any questions so far? Any questions?
So what was that? Is that the integration or the?
So I was asking, after we determined the most general antiderivative or the indefinite integral of the function that we were given, I was asking, because I needed to ease our way to the first the part 1 of the fundamental theorem of calculus, I was saying, okay, can we check the answer on definite integrals? And the answer is definitely no. But now can we check the the result or the function that we obtained when we calculate an indefinite integral? And the answer is yes. And the answer is yes always. So I copied the initial integral, and I copied our answer. And I said, okay, how do I check? We differentiate both sides. But what happens on this side, when I differentiate the integral, this piece and this piece go away. So I get the function back. And we differentiated the right-hand side, and we got this, and we show that they are the same. So, which means that the antiderivative, or if you want, the function that represents the indefinite integral is indeed correct. We differentiated this, and we got the function back. And this is what we did in 4.9, right? We were given a function, and we determined f of x, uppercase f of x. If I differentiate uppercase f of x, I get the function back.
So you're just proving that that's what that was.
Exactly.
Oh.
Yes. And it gave me a reason to talk about the fundamental theorem of calculus part 1 that clearly specifies that differentiation and integration are inverse operations. But we cannot show that with the definite integrals. We have to look at indefinite.
What's the
Yes.
integration again?
Okay. Finding an area under the graph of a function. That's one explanation. That's one explanation of the integration. Finding functions. I can be given, it's a very good question actually. I can be given on page, we will not have time to do this problem, but we can do it next time. So for example, perfect question. Thank you so much for asking. Water flows into and out of a storage tank. A graph of the rate of change, r of t, which is f prime. So the graph of f prime is given to us of the volume of water in the tank in liters per day is shown. This is the graph of the rate of change. If the amount of water in the tank at time t0 is 25,000, this is the derivative. Use the midpoint rule, which we talked about it, but we didn't finish, to estimate the amount of water in the tank 4 days later. So determining the area under the graph, so the positive area and the negative area, will give us how much water is still in the tank. And that will be the integral. Or in this case, because they're not really asking, they're not giving us the function, we will not be able to integrate because I don't have the function. So how will I determine the volume of water still present in the tank? By approximating it with rectangles. So they didn't tell us how many rectangles we choose. Right, so yes, or count the squares. So I will use probably 1, 2, 3, 4, 5, 6, 7, 8 subintervals. And I will come up with an approximation of the volume of water in the tank. Because we are given the graph of f prime. Reversing the operation will give us the volume. Okay, so it's a very good question. Okay, I know we only have 2 more minutes. Would you like to do one more quick integral?
Yes.
14. 14 on page 404. This is the integral from cosecant squared t minus 2e to t dt. Which function prime is cosecant squared or close?
Cotan t?
Yes, with minus. Very good. Minus 2. Which function prime is e to t? That's the nicest, isn't it? Can I